implications of the sensitivity conjecture.
Thanks. Yeah, it's really wonderful to hear how to speak about his beautiful result. And I was just struck when I saw it first, and it's such an elegant and beautiful proof from the book for such a long-standing conjecture. The sensitivity conjecture was, like, you could say, one of the big open problems in Boolean functions analysis for many years. And you know, Puya and others have beautiful surveys showing like a lot of equivalent formulation of this conjecture. So we knew that this implied a lot of things, but I guess one of the things that I'm going to talk about today are things that we didn't know that are implied by the sensitivity conjecture. And you really need to look into the proof and this notion of this lambda of f in order to get this new result. So they are application of the result in a white box fashion, I would say. So this is joint work with Scott Aronson, Shalev Ben David, and Robin Kotari. And I will talk about the decision tree model and the quantum version of it. And the main result is that the decision tree complexity, deterministic decision tree complexity, is at most quartic in the quantum query complexity. And this is optimal, and I will mention it later when we get to the result. And this improves the best relation between deterministic and quantum query complexity. The best power before our work was 6 power, now it's 4 power, and the 4 is the right answer. Okay, so I'm not assuming that you are familiar with these notions, so let's introduce all these notions. So we're talking about the black box model. So we think of our input x as a very, very long string, sort of similar to what we think in sublinear algorithms for probability testing. And this string x is sitting inside a black box. So it's a string of length n, and at every time step, we're allowed to query this black box at a coordinate I, and then we get an answer back xi from the black box. Okay, so we can ask, you know, what's the seventh coordinate? We get an answer back. Then based on the outcome, we may decide to query another coordinate, maybe 3, and third coordinate, and so on and so forth. And we usually would want to answer some questions about the string x sitting inside the black box. Does it satisfy some property or not? Does some function f on it equals 1 or minus 1? And we want to do it by making as few queries possibly adaptive to the black box, as few as possible. Okay. So this is what's called the query complexity of the function. So let's say that we have a Boolean function f mapping strings of n bits to 1 bit. We said that the query complexity of f is the minimal number of queries we need to make to this black box in order to know the value of f on the input x. Okay, and we want to take an upper bound that sort of would work for all possible inputs. Okay, another way to describe this model is a decision tree model, where a decision tree is simply this binary tree that you see on the right. At every time step, you're querying one variable. Let's say in the beginning, the root you're querying, in the root you're querying x1, right? And then, you know, if the value of x1 is 1, you go right. If it's minus 1, you go left, and you continue traversing this tree. You go down a path until you reach a leaf, and the leaf has an answer. You know, either the answer is positive or negative, and that is what you output. So this is a model of computation that definitely describes a Boolean function. So if you follow this decision tree model, this gives you a Boolean function. And for every Boolean function, you can build a decision tree that computes it. Maybe the depth would be n. Maybe you need to query all the coordinates. But in some cases, you can query less than on the, like the depth is less than n. And this really corresponds to the query complexity. If you think about it, by describing how you act depending on the past answers, you can write down for any deterministic algorithm that has query complexity D, you can write down a decision tree with depth at most D, and vice versa. So these are just two different ways of looking at the same model. And right, we denote by D of f, for a given function f, we may have many decision trees computing it. We denote by D of f the depth of the best decision tree computing depth, right? Or in other words, the query complexity of f. So in the second part of today's talk, we're going to talk about this notion of query complexity. We're going to talk about the deterministic version of it, which we already saw. And then we're going to talk about the randomized and the quantum analogs of it. Okay, so maybe let's start with like a few examples just to make sure that we're on the same page. So what is the decision tree complexity of the parity function? Okay, so I already wrote the answers, unfortunately, but think about it. Let's say that we want to know if the parity of a given string of length n, is it even or odd? So we must query all the bits. If we query all but one bit, then the last bit could change the value of the function. Right? So this means that the depth of a decision tree computing the parity function should be at least n, and we can always have figure out the answer if we query all the coordinates. Okay. So maybe a slightly more interesting problem is the OR function. So the OR function, we want to say either like is the string all, let's say, -1s, or there exists a coordinate for which this coordinate equals 1. Okay. So for this, we also need to query all the coordinates. And the reason is as follows. So no matter how we're going to adaptively choose which coordinates to read, if on the first n-1 queries we got -1, we still don't know the answer. It could be still the last bit that we haven't read is 1, and then the answer would be 1. Or it could be -1, and then the answer would be -1. So still for the OR function, we still need to read the entire input. Okay. Okay, so far it seems that all the examples that we have, we need to read the entire input to figure out the value of the function. But there are functions where we need to read only log n many bits, and there are functions that depends on all the input bits. So for example, let's look at the following address function. So the address function gets k plus 2 to the k input bits. So let's call the first k x1 up to xk, and let's call the last one y1 up to y2 to the k. So the first k bits define a number between 1 and 2 to the k. Right? You can think of it as a binary representation of a number between 1 and 2 to the k. And then look at the corresponding yj, where j corresponds to the number described by x. Okay, so this number points to one of the bits in y, and then we output this bit in y. Okay, so this is called the index function or the address function. We can think of like the first k bits as the index or the pointer, and the last 2 to the k bits as like an array. And based on the pointer, we are selecting one entry in this array, and we output this bit. So if we think about it, how would you implement it as a decision tree? You would query x1 up to xk. And once you query all of them, you just need to query one of the yi's. So here, maybe you'll query, I don't know, y1, and here you'll query y2 to the k. And then based on the answer of this yi, you would decide whether to accept or reject. So this tree would be of depth k plus 1, but it really depends on all the coordinates. So really, every coordinate could make a difference in one for some inputs. Okay. So maybe the last example is the nicest one. I want to play a game. Let's play a game with Prasad. Okay. So I want to understand the deterministic query complexity of the majority of 3 bits. Okay. So we have x1, x2, x3, and you want to figure out, I have a string in mind, and you want to figure out, whether the majority is 1 or -1. So you are allowed to ask me questions. So feel free to ask me questions.
First bit?
Sorry, I didn't hear.
What is the first bit?
Yeah, it's 1.
What is the second bit?
It's -1.
I still don't know. What's the third bit?
Okay, yeah, it's 1. Okay, so yeah, so you see that by answering an adversary could answer question in a way that the decision would still not be known, right? So Prasad, I'm sort of going to keep balancing the 1s and -1 in my answers until Prasad will need to ask all the questions in the end. So, and this adversary method is actually a way to show lower bounds on this deterministic decision tree complexity. And there's also a quantum analog of it, which we'll get to later. Okay. So I just want to say that all the things that we heard so far in Hao's talk are sort of motivated, were motivated initially and are still motivated by the decision tree complexity. And for example, box sensitivity is a complexity measure that was invented to lower bound the deterministic decision tree complexity. Okay. So let's talk about some other variants of this model. So we talked about deterministic algorithms. We can also talk about randomized algorithm or randomized algorithms that makes few queries. So this corresponds to a randomized decision tree. You can write it in 2 different ways. So on the left, you see that you have, every node either queries a variable or flips a coin. Okay. And by the depth, I'm looking at the longest path, and I'm counting only queries along this path. I'm not counting coin flips. Okay. But this is equivalent to just making all the random choices in advance. So you can sort of flip all the coins in advance, and then make all the rest of the decisions deterministically after flipping these coins. So basically, you can pull the randomness to the top of the tree and think of it as follows. You have some probability distribution over trees T1 up to Tm. Each of these trees is a deterministic decision tree of depth at most t, and this is describes a query algorithm that makes most d queries and uses randomness. Okay, so what do we want of this randomized decision tree? We wanted to compute the function with high probability. So we wanted to output for every single x, we wanted to output the value of f of x with probability at least 2/3. And this probability is over the random coins. Okay. And again, we can denote by R of f the minimal depth of a randomized decision tree that computes a given function. All right, so the randomized was sort of a segue towards the quantum analog of it. The quantum analog is the one that I would focus more in today's talk. Okay, so we talk about quantum algorithms. So let's start with the basics. So in quantum algorithms, the most basic element is a qubit. It's just a superposition over like a 0 and a 1. We have 2 amplitudes, alpha 0 and alpha 1, which are complex numbers, and the sum of the squares of the norms of these numbers equals 1. Okay, so for example, a qubit could be in this position where you have like 1 over square root 2, the 0 state, you're in the 0 state, or 1 over square root 2, you're in the 1 state. Okay, another option is the same, but the sign of the amplitude of the one state is negative. So you can also have negative coefficients, and you can also have complex coefficients. And more generally, you can look at the system of m qubits, and then you have an amplitude for each string of these m qubits. So you have 2 to the m amplitudes. Okay. All right. So if you're not familiar with this notation, this notation of this this thing, this cat notation, you should just, if you are familiar with linear algebra, you should just think of it as a vector whose only non-zero entry is the ith entry, and all the rest are zeros, and the ith entry equals 1. Okay, so it's just, this notation is just a fancy way of writing, this is correspond to a vector of dimension 2 to the m. Okay. So what can we do in a quantum algorithm? What can we do to a quantum state? We can measure it. When we measure a qubit or a sequence of m qubits, we would get the answer I with probability proportional to alpha I squared. Okay, and that makes sense because the sum of alpha I squares equals 1, so it is a probability distribution. And another thing that we can do is we can apply unitary transformation on our quantum states. Okay. And unit transformation also preserve norms, so it also preserves the fact that the sum of alpha I squares equals 1. All right. So what is the analog of the black box model, or like the decision tree model in quantum algorithms? So let's first, unfortunately, I don't have a decision tree picture to draw for you. So I go back to the first picture, the black box model. So how do we extend this black box model to the quantum setting? So recall that everything that we do, every transformation that we do on our state should be a unitary. So the most natural choice is to have the black box implement the following transformation. If I give it state I, then I want to get I want to get back the state I when I multiply the phase or the amplitude by xi. So if xi is 1, I'm not doing anything. If xi is -1, I'm like flipping the sign of the amplitude. Now notice that this preserves norms, right? So if I give it like if I give it this vector, then it either produces like this vector or this vector. So both of them has the same norm. But since I defined this transformation on the standard basis, it naturally extends to the entire space. And if I take a superposition over the question, so if I take superposition over these i's with amplitudes alpha i's, I get a superposition over the answers. This just follows by linearity of the operation. Okay, so in some sense, you can think of it as if we're querying the black box in superposition. Now, this may seem a bit weird because it seems like we are like accessing everything in just one query. But notice that when we measure, we collapse, right? So the fact that we are sort of have access to the entire string doesn't really mean that we can get the information from the entire string. You can also think of the randomized analog. So in the randomized analog, I can also query each coordinate with probability 1 over n. Then after one query, I have, I'm still depending on every coordinate, but I'm depending very weakly on every coordinate in the right. So So still for many interesting functions, this it's still hard to compute the function even with a few quantum queries to the black box. Okay, so for example, if you want to compute the parity of the string, you still need to query. You still need to make n/2 queries, so linear in n queries. All right. So
Avishay,
yes.
is it so this, for instance, does this include a query where I sort of try to learn a linear combination of the xi's, or somehow or do you always just learn a particular bit with some probability, each bit with some probability, or
Right. So you are getting, like, if you give the black box a superposition, you are getting a superposition over the answers, and you could apply then a unitary on that. So potentially, yes, it seems that you could, but it's not any linear combinations, right? So you are bounded to unitary transformations. So just to say, to compare it with the randomized model, you can also think of the randomized model as if you're getting a vector, and then you're getting a vector where each, maybe in the quantum setting, you'll go from like this thing to like ixi, because I don't want to have negative signs. But in the quantum setting, the vectors that you can get in the input and the output will be probability distributions, and the transformation would be stochastic matrices. And here you would get vectors of norm 1, and the transformation would be unitary transformations. So you can also view randomized algorithm in this model.
I guess the input and output in the picture you drew, it seems like they're both in the same basis. At least the notation seems to suggest that.
Yeah.
The input and output is in the same basis, and you measure also in the same basis. But I guess the I in the input and the I in the output are different or something.
So we can measure in any basis. So you can apply a unitary transformation after a query. Okay, so maybe let me say, how does a general quantum query algorithm looks like, or a quantum decision tree, how it looks like. So you start with some, the simplest quantum state, like the all-zero string. Okay. And then you apply d times the following thing. So you first apply some unitary transformation in your state that doesn't depend on the input x. And then you query x. Then you apply this oracle unitary. Okay, and then again, you apply some arbitrary unitary transformation, and then you query arbitrary unitary transformation, you query, so on and so forth, and you do it for d times. In the end, you apply another unitary and you measure. Okay, so you get a string. Based on the string, you decide whether to accept or reject. Okay, so that's like the general model. Right. And you can show very nice things about this. So Beals et al. Showed that, if you look at like the amplitudes of the vectors, you look at them as function of the input x, then every time you make a query, you increase the degree by 1 at most. So therefore, if you do d queries, the degree of the entries and every time you apply a unitary, you're just doing a linear combination, so you don't change the degree. So the degree of the entries as polynomials in the input x is d. When you measure, you take the squares. So the degree, like the probability that you output something is like a sum of squares, which means that it's a polynomial of degree 2d. and this gives rise to connections between quantum query complexity and the degree of function as a polynomial. Yeah, okay. So I guess I mostly wanted to introduce this model. I'm not sure that we're gonna dive too deep into it further. Okay. So we discussed like the deterministic query complexity, the randomized, the quantum. We can also talk about the non-deterministic version. In the non-deterministic version, for example, I want to prove to Prasad that the value of majority on my string is 1. So then I say, please look at coordinates 1 and 3, they are both 1. So then I can only reveal 2 coordinates, and I'm convincing Prasad that the value of majority is 1. Block sensitivity we already saw in house talk. There's the degree, which we also saw, and there's the approximate degree. I guess I haven't defined that. So the approximate degree is you want so you have some Boolean function. You want some polynomial, multilinear polynomial, and you look at how it maps like the Boolean inputs. So you want for every x, and you want this polynomial to be of minimal degree, and you want for every x the value of the polynomial and the value of the function to be not too far apart, let's say at most 1/3 apart. And you're looking for like the minimal d such that there exists some p where the degree of p equals d. Okay, so that's the approximate degree. Obviously, if we can compute the function exactly as a low degree polynomial, then we can also approximate it by a low degree polynomial, but sometimes this approximate degree is smaller. Okay, so these are all interesting complexity measures that were studied a lot in the past few decades. And this beautiful line of work by Nisan, Szegedy, and Bill, Spurman, Cleve, Muska, and Wolf, they show that all of them are equivalent. They are like this happy flock that we saw in the previous talk. What do we mean equivalent? For each 2 complexity measures here, if we look at Boolean functions, one complexity measure is bounded by another to the 6th power. Okay, and in some relations we can improve the power from 6 to 2 or even 1, but okay, but all of them are polynomially related. And the question of the sensitivity conjecture, another way to phrase it, is whether sensitivity can join this party, whether sensitivity is also polynomially related to all the rest. And right, and now we know that the answer is yes, right? So now we know that based on this amazing result, we know that sensitivity is polynomially related to all these complexity measures. All right. So what next? So I want to introduce a new complexity measure. I guess it was already introduced in the previous talk, and it's quite natural, and it's really important in the proof of the sensitivity conjecture, right? So let's say that we have a Boolean function. So I drew here an example of a Boolean function. So, right, so I have all the 3-dimensional hypercube, and I marked some vertices with +1 and some vertices with -1. And this defines a Boolean function. So for every input, I'm defining the value of the function by this drawing. And the sensitivity graph corresponding to this function is I'm just taking edges in this hypercube for which the 2 ends have different colors. Right? Or in other words, I'm taking edges such that if I change the coordinate corresponding to this direction, I'm changing the value of the function. So for example, the function on the left is the majority function on 3 bits, and the sensitivity graph is exactly this graph, where this bipartite graph. Okay. So how do I formally define it? So you just connect two edges if they are neighbors in the hypercube, meaning that they differ on exactly one coordinate. Their Hamming distance is 1, and the value, the f value of them on them is different. Okay. And this sensitivity graph is exactly the graph that Huang was talking about, right? So this is the graph that you get from this Gotsman-Linial transformation, because when you multiply the graph of the function with the party, and you take the component of the 1 and the component of the -1, is exactly the graph that you would get. I mean, it's a simple exercise to see. All right. So what would be the sensitivity? The sensitivity of a function? It's just the, you know, if we look at this graph g of f, it's just the maximal degree. And now notice that degree means something else than degree as a polynomial. So it's the degree in the graph. It's a maximal degree in this graph. Okay, so for example, here the sensitivity is 2, because you can see there, like, the maximal degree of this graph is 2. Right. So this vertex has 2 neighbors, and there's no vertex with more than 2 neighbors. All right. So looking closely at the proof of Huang, he showed that the degree, like the degree as a polynomial of any function, is at most the sensitivity squared. But you can actually break it down into these 2 parts, where the degree is at most this lambda of f squared. And the second part is that lambda of f is at most the sensitivity. And the second part is really simple. The first part is where the ingenuity came. And what is this lambda of f? Lambda of f is the maximum eigenvalue of the adjacency matrix of G of f. Right? So it's a very natural complexity measure of a Boolean function. You look at all the sensitive edges defined by the function, and you look at, you know, the spectrum of this adjacency matrix, or the maximum eigenvalue of this adjacency matrix. All right, so what I'm going to show you next is just, you know, simple observations, but they resolve long-standing Emory questions. All right. So really, this lambda is the new character in this story, and it seems to be a very central character that we haven't. Well, maybe some people have noticed, but it didn't receive a lot of attention. Right, the main result of Huang is that we have a lower bound on lambda. Lambda is at least square root the degree, right? And based on that, we can achieve the sensitivity conjecture. And right, so, and also Huang showed us that lambda is lower bounded by square root the sensitivity. And the reason is as follows. So if you have a vertex with s neighbors in this graph, then the eigenvalue of this graph is at least square root s. And it's a simple exercise to see that the eigenvalue of a star with s edges is square root s. And you know, if we have more edges, then the eigenvalue can only be higher. So that's why, right, if we have s edges, then the eigenvalue, the top eigenvalue, is at least square root s. And I guess a very intriguing question is whether we can also lower bound lambda by square root of the block sensitivity. If this is correct, then we would get that, you know, we know that this is upper bounded by the sensitivity. Then we would get exactly the fact that block sensitivity and sensitivity are quadratically related, right? Which was conjecture I guess, by Nisan and Szegedy in their paper. And also we know that this is the best possible due to this example by Rubinstein. Okay. What about upper bounds on lambda? Well, we also saw this upper bound, which is again a simple thing. You know, if the maximal degree is S, then the eigenvalue is at most S. Okay, so this is simple. So we get from this that lambda is at most sensitivity, and sensitivity lower bounds block sensitivity, certificate, and decision-tree complexity. So lambda basically lower bounds all these measures. And our observation is that lambda also lower bounds this quantum query complexity. Okay. So I'm going to talk about it in the next slide. But I guess there are two things that are still open. So what about lambda versus degree? Does lambda lower bounds degree? And does lambda lower bounds approximate degree? So like when we published our manuscript a few months ago, we called these like conjecture 1, conjecture 2. And a very exciting recent development from like the last few days is that it seems that we know now how to prove these results. I'm not going to talk about it because it's really still a little bit half-baked, but based on discussions with Sravas Rao, he gave a beautiful approach how to get this conjecture, and we were able to extend it, in this joint collaboration with Scott Aronson, Shalev Ben David, and Robin Kutari. We were able to extend it to this thing. So really, lambda lower bounds all the complexity measure that we, okay. Caveat, we still need to verify all the details, but assuming that this indeed works, lambda lower bounds all these complexity measure, but it's not that small, right? It's at least square root of the degree and at least square root of S. So it's a very nice complexity measure, and it will allow us to get better connection between the other complexity measures. Okay. So just based on what I told you so far, you can get that for any Boolean function, the degree is at most the quantum query complexity squared, or rather that the quantum query complexity is lower bounded by square root of the degree. Okay, so the first ingredient is, this result by Huang. And the second ingredient, I said it follows from the result of Ambinis and Barnum, Sachs, and Szegedy. Specifically, so there's a lot of ways to lower bound quantum query complexity. Actually, many of them are equivalent. So unlike what Juan said, sometimes we have different names for the same complexity measure, and we realize it later. So one method to lower bound quantum query complexity is called the spectral adversary method. I'm not going to go into the proof of this, but basically, you need to maximize the following thing. You need to find the best matrix, I guess capital gamma. This is a 2 to the n by 2 to the n non-negative matrix. And the only non-negative entries of it are for, x, y, such that f of x is different than f of y. Okay, so this is the thing that you are maximizing over. And you're looking at the spectral norm of gamma divided by the spectral norm of gamma when you only keep the coordinates for which x and y differ in the ith coordinate. Okay. I guess, sorry, this is not completely right. I guess this is the right thing. So you just keep entries where x and I differ in the ith coordinate. Okay, and this lower bounds quantum query complexity. I will not show you the proof, but the point is that, it's very simple to see that lambda of f lower bounds this thing And the reason is just take this capital gamma to be the adjacency matrix of G of F. The top eigenvalue of this thing is lambda of F. And what is this thing? So if I'm picking one direction and I'm just keeping the edges in this direction, right? So what will be the top eigenvalue of this adjacency matrix? Well, I have only at most one edge touching every vertex. So the degree is at most 1 for each vertex. So the top eigenvalue is at most 1. So therefore, the spectral adversary bound is at least lambda. And this also follows, if by closer inspection, it also follows from the slightly previous work of Ambanis, because we are not really using the full power of this method. We are just picking this capital gamma to be a 0-1 matrix. And this follows from the previous result of Ambanis. Okay, so now how do we get the connection between deterministic decision tree and quantum query complexity? Well, we just combine it with known results from the literature. So Midriani showed that the deterministic decision tree is at most block sensitivity times degree. Nisan Szegedy showed that block sensitivity is at most approximate degree squared. And Beals et al. Showed that approximate degree lower bounds quantum query complexity. And this is what we discussed, right? That for every quantum query algorithm, you get a polynomial that approximate your function. So if you combine all these things together, you get that the deterministic query complexity is the most quartic in the quantum query complexity. And I should say, okay, so let's maybe look at a few examples. So when f is the OR function, we said that the deterministic complexity is n, but it turns out the quantum complexity is square root n. And this is a well-known result. It's like called Grover's search. Basically, it tells you, you can find a 1 in a string in times square root n if you have a quantum algorithm. And the lower bound is by Bennett, Broussard, Bernstein, Vazirani. So here you can see that there exists a quadratic separation between quantum and deterministic. It was conjectured for many years that this is the best, but actually then came this work of Ambanis et al. They showed that there's a quartic separation. And Shalev Ben David, Robin Kotari, and Scott Aronson also showed a super quadratic separation between randomized query complexity and quantum query complexity. Okay. So basically, this settles the best separation between deterministic and quantum query complexity. The best separation is 4, and we have a matching upper. I just want to mention a few more consequences of the first theorem, the one about the relation between quantum and degree. You can very easily get by that the quantum query complexity of OR is at least square root n. And that's just because the degree of OR is n. Right? We know that theorem 1 tells us that Q of f is at least square root the degree of f. So you get this result by BBBV really immediately from this theorem. And you also get that if you compose OR with ends, so you take an OR of ends, you get a lower bound for that as well. And this took more work. I think this was proved for the first time by Ambanis. And more generally, if you have any formula, the Morgan formula, that only reads every variable once, then you get a quantum lower bound of square root n. And remarkably, there's also a quantum upper bound of square root n. So we know the quantum query complexity of every De Morgan formula that reads every input 1, it's square root n. I believe that these are all known results, but you get a very simple proof for all these results, because the degree of these functions is at least n, is exactly n. Sorry. Okay, another thing that we get is a sort of resolution of the quantum analog of the evasiveness conjecture. This is a long-standing conjecture by Andrea, Karp, Rosenberg. They conjecture that if the function is a graph property, I mean, you think of the input as indicating for each edge whether it's in the graph or not. And the graph property is, something like, is a graph free colorable? Is a graph connected? Does a graph contain a cycle of length 4? I don't know, things like that. So these are things that do not depend on the naming of the vertices. So that's a graph property. And the conjecture is that if you want to compute that for any graph property, you have to query all the edges. Okay, and currently the best known lower bound is that that you need to query at least a constant times all the edges. Okay. There's also an analog for the randomized setting, saying that if you want to answer with high probability, you need to query at least a constant times the number of like a constant fraction of the number of edges, and the best and non-lower bounds is polynomially related, so it's like n to the 4/3 instead of n squared. And for the quantum analog, what we can show very easily by theorem 1 is that you need at least n queries. And the reason is that, so based on this result, you can also show, like if you adapt it, you can show that the degree is at least n squared. This is a result, I forget, but it's Ron Rivest and another guy that I'm forgetting the name. And since the degree is quadratic, the quantum query complexity is at least linear. And this is also tight because the property, the graph property could be, are you containing an edge? And then you can do Grover search. Are you the empty graph? So it's very simple consequences of Huang results that prove long-standing conjecture. So now I wanted to show you this table. So we talked about all these complexity measure. There's a nice table. I guess we borrowed it from previous paper by Aronson, Ben David, and Kotari, and now we updated it. So you can see it's for every 2 complexity measures. Let's look, I don't know, here, maybe. So you can see this entry. It says like 2 numbers, 2 and 3. It says you should interpret it as follows. We know that for every Boolean function, the deterministic query complexity is at most the randomized raised to the power 3. And we know that this cannot improve beyond 2. We know that there exist some functions such that the deterministic is at least the randomized square. Okay. So, okay, I'm not going to go into all the details here. I just want to say that, we improved a lot of entries, like just one result improved all the entries marked in green in this table. And based on this new work with Ben David, Kotari, and Aronson, we get all the red ones. And I guess if we, based on this new result that I was promoting, that we were like in the middle of writing, we would get a bunch of new ones as well. I want to point out that if you are interested in seeing this table, there's a very nice website that a student in Berkeley wrote. The name of the student is Alex Hu, and you can see the, oops, sorry. You can see the link here, and I will post the slides later so you can look at the link. And you can also insert new relations that you have, and it will sort of find all the implication of it, because for a lot of these entries are sort of, you combine a lot of known results. Okay, so this table is smart. It's sort of, you give them like 5 results and it gets you all these big tables. Right, so let me finish by mentioning that, you know, this table is still not complete, and there's a few nice open problems that I want to highlight more than others. Like, what is the best separation between randomized and quantum query complexity? We figured out between deterministic and quantum, but not between randomized and quantum. And here we know that the exponent should be between 2 2/3 and 4. And it seems likely that it's 2 2/3 could be improved to 3. And this is another work based on work of Nisan and Aronson. But we still don't know what the right answer. Maybe 3 is the right answer. We discussed this block sensitivity versus sensitivity. We know that the exponent should be between 2 and 4. Deterministic decision tree and block sensitivity, it should be between 2 and 3. Actually, this was like highlighted for many years as like the way to get the best relation between deterministic and quantum query complexity. If you can show that this is the right answer, you would also get this quartic relation. And finally, so if you look at this graph, so this is like a graph of all these complexity measure. If you're higher, it means that the complexity measure is bigger than the previous one. So deterministic query complexity is always bigger than randomized, which is always bigger than quantum, which is bigger than approximate degree. So really, lambda sits at the bottom and deterministic decision tree sits on the top. So we really want to get like the best, like if we can get like the best relation between these two, maybe it's a 4th power, then we would get that all of them are related by a 4th power. So here, this is between 4 and 6. And if you're interested in this topic, I really recommend this survey by Burman and de Wolf. It's really a wonderful introduction to this area, and also to the quantum model, which I was always afraid of going into, but this survey is so nice that it's really inviting to this field. And there's like so this is like from 20 years ago, but still very relevant. But a more recent work by Aronson, Ben David, and Kontari talking about separations using cheat sheet is maybe another reference that is worthwhile looking into if you're interested in these topics. Yeah, I guess that's it. Thanks. All right. Yeah, I guess it's been a long day, so.
Any questions?
Yeah.
So I had a question. The SA bound, is that SA, the spectral adversary, is that equal to the quantum query complexity?
Right. So no, you could. There is a more refined lower bounds in this paper of Barnum, Sachs, and Szegedy that exactly equals. So basically, they capture quantum query complexity by a semi-definite programming, and this is like the dual. But this is like a relaxation of it. It is easier to handle, but it's not tight.
Okay.
Yeah.
So there's a question on the stream. Yuval asks, are there any applications between complexity measures, of relations between complexity measures?
I mean, we usually want to know, right, what is the query complexity, what is the quantum query complexity, randomized, deterministic. So usually, like sometimes due to these connections, we get lower bounds and upper bounds on precise measures. For example, we want to understand if Grover search could be improved. No, it cannot, because we have this lower bound that the approximate degree is at least square root 10, and therefore the quantum query complexity is at least square root 10. So I guess maybe in nailing down the query complexities, these are all like lower and upper upper bound methods.
There's another question. Oh, there's another question by Subhayan. Is there any connection with these new bounds for quantum communication complexity of total functions?
Right. So usually when you have a separation, I mean, we talked about relations more, but usually when you have a separation, you can lift it to the communication complexity. It could be that in the communication complexity, you have bigger separation between these analogs. So I don't see immediately what you would get by these relations, but I'm not an expert on these lifting results and communication complexity results. So some, yeah.
Okay.
All right. Thanks for sticking for 2 hours.
Yeah, thanks for the talk.